Okay, let's take a look at reciprocal functions. We're on page 479 in your workbook. And reciprocal functions, we can see that the definition is provided for us. The reciprocal function of f of x is simply 1 over f of x. Of course, we recall we can talk about reciprocals with fractions. Usually it's brought up when we talk about dividing fractions. We say to divide a fraction, we multiply by its reciprocal. So if the function has the equation y equals x squared minus 5, then the reciprocal function would be y is equal to 1 over x squared minus 5. So these are things that we can actually graph as well. So why not? Looking at the exploration then. So they've taken the function, simplifying a little bit, of just y is equal to x plus 3. And so they said, well, what's the equation then of the reciprocal function? The reciprocal function then is, of course, y is equal to 1 over x plus 3. And so you can then go ahead and graph those, or I think they've actually shown you what the graph looks like. The graph for y equals x plus 3, of course you guys recognize slope of 1, y-intercept of 3, x-intercept of negative 3. If you build the table of values, so there's our x values, and they're just saying partial table of values in y because x is an element of the reals. So these are just a few of our x values, and then the corresponding y values for when we're talking about y is equal to x plus 3, and there they are. Then we get into 1 over x plus 3, and so then those are just the reciprocals of these values in the second column then. And if you go ahead and you were to take the time to plot them, or if you were to use your graphing calculator and plot that reciprocal function, then this is what it looks like. So plotting that reciprocal function using your graphing calculator, obviously some of you have figured out how to input a fraction directly into your calculator. If you're not using that function, then please make sure that when you enter that into your calculator that you're putting brackets in the denominator as well. So why is it that your graph looks like this, and is a few things. So let's take a look, and we'll just follow what how they guide you, and then I'll add a little bit to that as well. So completing the following statements using the graphs and table of values. So I'm going to just hit pause, see if you can figure out what some of these are on your own, and then come back and I'll talk you through them. Okay, so the y-intercept of f of x, so just looking at our regular function, the y-intercept we can see is 3. So of course that happens when x is equal to 0, so y is 3. The x-intercept of f of x when y is 0 is x is negative 3. So then corresponding, the y-intercept of 1 over f of x is of course then 1 over 3, and that's it right here. The equation of the vertical asymptote of 1 over f of x is x is equal to negative 3. So I'm guessing that some of you guys may not have gotten this part of it. What is a vertical asymptote? An asymptote is essentially a fixed line that a graph or a curve will approach but will never cross. And so some of your calculators will actually draw that in. And so what that is if we wanted to draw this in, this is our vertical asymptote right here, and the equation of this line that represents the vertical asymptote is of course x is equal to negative 3. So key thing there is, where does the vertical asymptote occur? The vertical asymptote occurs where the x-intercept is. Okay? So vertical asymptote here x-intercept, and could there be more than one? Of course, if we're talking about the original function being a quadratic, then you may have two x-intercepts, in which case you'll have two vertical asymptotes. So where the x-intercepts are in the original function. Okay. The next really key thing about reciprocal functions is the fact that there are points where that appear on both graphs, and these points are called invariant points. And even if you take a look at the way the wording is put together, invariant, not varying, not changing, so exactly the same. And so what are those points then? Those points we can see right here. Happens when x is equal to -2, y is 1. And y is 1 on both of them, so right here, this point on this graph is right here, whereas the other one is at -4 and -1. So these points occur at exactly the same place. So if I was actually to take this graph of the reciprocal and transpose it on top of my other graph, those 2 points are exactly the same. So invariant points that are the same in both functions. The horizontal asymptote, so you can see again, so where does that occur, is right there, and that is going to be at your x-axis, so when y is equal to 0. So it approaches, but it never touches. So complete the following. When f of x is equal to 0, the graph of the reciprocal 1 over f of x has a horizontal asymptote. Okay. And that happens at y equals 0, right? That is your equation of line for your x-axis. As f of x approaches positive or negative infinity, the graph of y equals 1 over f of x approaches closer to the horizontal asymptote. Okay, and so why is that? If you think about it, what's happening here is as our y values are getting larger, so if you think about 1 over f of x, as that denominator gets larger and larger and it approaches infinity, then what happens to this value? So as we get closer to positive infinity, then this value is getting smaller. This represents a very, very, very small value, and that's what's happening right here. Versus the other case, of course, is if it's 1 over negative infinity, then it is also getting smaller, but on the other end right here. Okay, so just a couple of things to point out before we go on. So with this, if I'm given just to add to this, because you'll likely have to do this during your homework, if you're given the graph and you're not given the actual function itself, I didn't know that y is equal to x plus 3, how could I draw the reciprocal function of this? So the steps that I would be going through is a couple of things. One, I know that the x-intercept is -3. What does that tell me? It tells me that there is going to be a vertical asymptote here. So I'm going to draw that in right away. Next thing that I know that my invariant points happen at y equals 1 and y equals -1. So where are those on the graph? Right here and right here. What else do I know? I know that there's a horizontal asymptote that's going to occur at the x-intercept, or sorry, at the x-axis, y equals 0. One other thing that I know is because the y-intercept is 3, the reciprocal then is going to be 1 over 3. So that will end up right here. So knowing all of those things, I can then put together my reciprocal function. It passes through the invariant point, passes through the y-intercept, and it never crosses the asymptotes. Okay. And there it is. Similarly, if I'm given the reciprocal functions, what do I know? Well, I know that where my vertical asymptote is, that is my x-intercept. I know where my invariant points are, and I also know this point right here is my y-intercept, and so that should we can approximate that, but at the same time right here I can already see these 3 dots, and so then that tells me that it's got to pass through those points, and so there's my line, there's my original function then. So we should be able to work with both, either given the original function, even if you're just given the graph, you should be able to determine what the graph of the reciprocal function is, and on the opposite end, if I give you the reciprocal function, the graph, you should be able to draw in the original function. Okay, let's turn the page to page 480. So again, here they have it, where they've given you the original function of y equals x squared minus 4. So the equation of the reciprocal function then is of course 1 over, so y is equal to 1 over x squared minus 4. So they've once again given you a partial table of values, and so right here, this gray one, or the lighter colored one, that is your original function. So that is your y equals x squared minus 4 versus all of these extra little bits here. That is your reciprocal function of 1 over x squared minus 4. So again, hit pause and fill in those blanks there. So if we take a look at answering some of these questions, so I've outlined the original function y equals x squared minus 4 in blue, so we can clearly see that the y-intercept of that original function is negative 4. Because of that, the y-intercept of the reciprocal is going to be negative 1 over 4. So reciprocal, remember that doesn't change the sign, it's just taking 1 over whatever the function is. Okay, the x-intercepts, we've got 2. We know that if we factor y equals x squared minus 4, we would have y is equal to x plus 2 and x minus 2. It's a difference of squares. So if we're looking for the x-intercepts, we set y is equal to 0. So then that tells us that our x-intercepts are, of course, plus or minus 2. So positive 2 and negative 2. So remembering again that your x-intercepts then tell you what your vertical asymptotes are going to be, which are then your equations, which are x is equal to positive 2 and x is equal to negative 2. The horizontal asymptote, again, is going to be y equals 0, which is your x-axis. So let's take a look at that then. If I was to draw in my vertical asymptotes, here I see my x-intercept of negative 2, so there's the one vertical asymptote, and I'll label that as x is equal to negative 2. Here's my other one right here, and again, drawing that in, just being careful to show that x equals 2, that your reciprocal function is not crossing that vertical asymptote. And then again, we've got our horizontal asymptote, which is at our x-axis, so that is the line y equals 0. Because we've got our y-intercept at negative 4, then in our reciprocal function, again, we know that it's negative 1/4 as well. So other things to pay attention to, I don't think I highlighted it before, but notice right here again, and yet another reason why our vertical asymptote is at -2 and +2 is because, of course, when x is those values, y is 0. When we take the reciprocal, well, 1 over 0 is undefined. So it's impossible to actually have an ordered pair, a point, when y is equal to 0 for your reciprocal graph. So looking at the invariant points, so they don't actually show that on the table itself. We can skim through, and what are we looking for again? We're looking for y is equal to 1 or y is equal to -1. We're not seeing that there. So what we can do, though, is we can actually still mark that on our graph. You can see that in a couple of ways. One, you can see where the intersection is. The other part too is we look at, here's y equals -1. If we go across, there it is, y equals -1, and there it is again. At y is equal to +1, and there's our intersection here. And those 4 points, I'm in a different color, then it is green. So those 4 points there are points that occur on both the original function as well as the reciprocal function. If we wanted to calculate those algebraically, what do? Well, we substitute in y equals 1 and y equals -1, right? We recognize that we've got y is equal to x squared minus 4. So if y is equal to 1, then that means that 1 is equal to x squared minus 4. So x squared is equal to 5. And so x is then equal to plus or minus the square root of 5. On the other hand, if y is equal to -1, then we could say that -1 is equal to x squared minus 4. So then 3 is equal to x squared. So x is equal to plus or minus the square root of 3. So then that tells us that our invariant points then are, well, we've got +5 and 1, -5 and 1, as well as +√3 and -1, and -√3 and -1. And so those are the exact coordinates, and your calculator's not going to give you those exact values again, but that's how we can easily calculate it algebraically. Remember, the alternative is, I don't think you're going to want to do this, but because those values occur in both the reciprocal as well as the original function, we could also substitute using y is equal to 1 over x squared minus 4, in which case you're solving when y is equal to 1, so you're solving 1 equals 1 over x squared minus 4, as well as, of course, -1 is equal to 1 over x squared minus 4. But the original function is obviously a lot easier to use. So completing the following then, so when f of x is equal to 0, then of course we've got vertical asymptotes. So what is that essentially saying? When y is equal to 0, we've got vertical asymptotes because we can't have 1 over 0. As f of x approaches positive or negative infinity, then the graph of y equals 1 over f of x approaches closer to the horizontal asymptote, and our horizontal asymptote has the equation y equals 0, because of course this is at our x-axis. Okay, so the next page actually gives a nice little summary for you. It's a little bit confusing, but I think the bottom half of the page gives a little bit of clarification, and I'll give you guys another summary as well. So first off, when f of x is equal to 0, the graph of y equals 1 over f of x has a vertical asymptote. And so the x, remember, that is your x-intercept in your original function. That's your vertical asymptote. When f of x is positive, then of course the reciprocal is also positive. When f of x is negative, the reciprocal is of course also negative. When f of x is equal to 1, then the reciprocal is equal to 1. When f of x is equal to negative 1, then the reciprocal of course is also equal to negative 1. So this is emphasizing your invariant points. As f of x increases over an interval, then what happens? Remember, here it is. It's showing that our denominator is getting bigger. And so when your denominator is getting bigger, then the reciprocal function will actually decrease over the same interval. As the denominator gets smaller and smaller, then your reciprocal function 1 over f of x will of course increase over the same interval. When f of x, or when the value of your function approaches 0, then the reciprocal function approaches positive and negative infinity, and the graph of 1 over f of x approaches a vertical asymptote. And similarly, when your f of x, when the value of your function approaches positive or negative infinity, then the reciprocal function approaches 0, and the graph of the reciprocal approaches a horizontal asymptote. So there's a lot of new terminology in there. So just helping with you guys to simplify that a little bit. The zeros of the original functions, remember, what are they ultimately referring to? The x-intercepts of your original function become your vertical asymptotes of the reciprocal. You definitely want to mark in your invariant points, so determine either by graphing or through algebra determining where x is when y is 1 and when y is equal to negative 1. So you want to solve for x. Okay, and the y-intercept of the reciprocal graph is going to be the reciprocal of the y-intercept on the original graph. So if you've determined that the y-intercept is 4, then of course, they've actually kind of given that to you in number 4. If y is equal to 2, and that happens to be your y-intercept, then of course in the reciprocal it would be y equals 1/2. Okay, so let's take a look at some additional examples right here. So the graph of y equals f of x is shown, and the x-intercept is 2, the y-intercept is 3, so using the suggestions, try to go ahead and sketch the graph. So hit pause if you want to give that a shot on your own and see what pieces you can put in. So obviously, what are you looking at? Think about your invariant points. Think about your vertical and your horizontal asymptotes. Think about your y-intercept and see if you can put that all together. So hit pause and then we'll come back. Okay, so here we go. Right away I see that the x-intercept is 2, so remember the x-intercept tells me where I've got a vertical asymptote. So I'm going to draw that in, label that, so this equation of this line is x is equal to 2. What else do I know is I know that I have a horizontal asymptote at the x-axis at y is equal to 0. So I'll draw that in as well. Other things that I know my invariant points. So at y equals 1, they've drawn in that line for me, so that helps me to identify these invariant points. They've also drawn in y equals negative 1, but you can see that the original function doesn't go through y equals negative 1, so there's no invariant points at that particular spot. What else do we know? We can see that the y-intercept is 3, so if we take the reciprocal of that, then the y-intercept of the reciprocal graph is going to be at 1/3. So that's approximately right here. So what do I know is as these y values are increasing, then the reciprocal of that is actually going to be decreasing. And so this is going to follow along the asymptote, getting closer and closer, but never crossing. And this is going to continue up along towards the vertical asymptote, and the same thing on the other side then. And that is your reciprocal function. So filling these in, what's after the fact? So the y-intercept of the graph is going to be y is equal to 1/3 as well. If we know that, if I'm looking for the equation, remember right here, I know some of you guys would end up doing 1/3 x minus 2 squared, but that doesn't look too pretty with the denominator there. So something to remember is that if I've got 3/4 times x minus 2 all squared, y is equal to that. Y is actually equal to, remember that's all just in the numerator, so that's 3 times x minus 2 all squared over 4. So if we were to take the reciprocal, then it's 4/3 times x minus 2 all squared. So that is your reciprocal function then. Okay, try putting that into your calculator and you should see that come out just the way that we've drawn it as well. Okay, so again, try that for class example number 2 with the quadratic. So hit pause and then we'll come back together in a moment. Okay, so drawing this out, we can already see that my x-intercepts are 1 and -2, so that tells me where my vertical asymptotes are, so we'll sketch those in. Hopefully if you've got a ruler, that would help. It's shocking that I haven't brought that up sooner. Okay, so draw in our our vertical asymptote. So we've got x is equal to -2 and x is equal to 1 as our vertical asymptotes. Our horizontal asymptote, once yet again, is at y is equal to 0 at your x-axis. What other information are we looking at? We're looking at our invariant points, so taking a look at where y is equal to 1 going across to my graph, then I can see here is y equals 1. Once again, y equals 1 here, y equals -1, and y equals -1. So there's 4 invariant points in this particular case. What other piece of information is going to be helpful for me? I can actually gather 2 pieces of information. One is they've given us the max point, which is 2. Remember, we're not changing the x value, it's only the reciprocal of the y value. So at this particular point here, where the x, we're not sure, we can probably estimate that at 1/2, but at -1/2, y is 2, so the reciprocal of 2 is going to be 1/2, so that tells me that this is a point on my reciprocal function as well. Here's my y-intercept, almost at 2, so again, this is going to give some more information of where my y-intercept is going to be. So again, not a whole lot of options. I have to cross through that y-intercept. I have to cross through that now reciprocal of my max point. Not allowed to cross my vertical asymptote. So here we go, going through there. So there's part of it, and again, showing these aspects, and there is is our reciprocal function then. So let's answer the question. So we've sketched our reciprocal function, state the equations of the asymptotes. So we already did that. The vertical asymptotes are x equals -2, x is equal to 1, and then our horizontal asymptote of y equals 0. The point a 1/2 lies on the graph, so state the value of a. So what do we know is if a comma 1/2 is on your reciprocal, so if it's on 1 over f of x, then that means that a2, reciprocating it back, must be on your original function. So what do we know is that a2 has to be your vertex, and since the vertex is halfway between your x-intercepts, then what do we know? Your x-intercepts being -2 and 1, so let's figure out what that point is then. So to figure that out, halfway between -2 and 1, so add them together, divide by 2, and that gives us -1/2. So that tells us that, so a is equal to -1/2, and that is that point right here, -1/2. Okay, awesome. Let's move on to our last example then. Oh, sorry, this is getting long. But as I mentioned, lots of little things to emphasize with you guys. So for this one, we've got the graph of g of x is equal to 1 over f of x. That's shown. So what they're telling you essentially is here is your reciprocal function. So the maximum point on g of x, maximum point on your reciprocal function is at -3, 2. The y-intercept of your reciprocal function is 1/5. So if you want to hit pause and try to do the graph of that based again on what you know about your y-intercept, the maximum point, as well as your invariant points, then give that a shot. So hit pause and come back in a moment. Okay, so here we go. I've written down a few things that I had mentioned already to assist you with graphing. So your minimum point they've given you is -3, 2. So that tells us that the original, since this is a reciprocal, then the original has a minimum point of -3 and 1/2. So that's going to put us somewhere, whoops, right here. The x value, remember, is not changing. The y-intercept of f of g of x is 1/5, so that means the y-intercept of f of x is going to be at 5. We have invariant points at y is equal to 1, so there's one right here and the other one right here. We don't have anything at y equals -1. It doesn't exist in this particular case. We also have symmetry at your vertex, and so since we know 0, 5, we can come over and we know that 6, 5 is also a point as well, and that now gives us enough information that we can draw our quadratic and our original function f of x. So let's take a look. If f of x can be written in the form y equals a times x minus p squared plus q, so that's your vertex form, determine the values of a, p, and q. So a few of these we already know. We know that pq, our vertex, is -3 and 1/2. We also know a point, xy, could be 0, 5. We could also use 6, 5 for that matter. So we can then solve for a. So if we know that our vertex form, we've got the formula, substitute everything in. So y is equal to 0 plus 3 all squared plus 1/2. And solving here, so this is 10 halves minus a half, so that's 9 halves is equal to, whoops, I'm missing my a. Is equal to 9a, and divide both sides by 9. Dividing by 9, course, the same as multiplying by 1/9. So then that leaves us with just a is equal to 1/2. So in that particular case, our function then is equal to 1/2 times x plus 3 all squared plus 1/2, or if they're just asking what are the values of a, p, and q, another way to state it would simply be to say that a is 1/2, p is equal to -3, and q is equal to 1/2. Okay, awesome. Good job, guys. And what I would like to do, because I think there's a lot to digest, the best thing to do is actually to complete all of the questions. So that would be from page 484 to page 489, numbers 1 through 13.